Okay. This Fermi question is about calculating how powerful the sun is. The Earth receives 1,400 watts of radiant energy per meter squared from the sun, at our distance from the sun, which is 93 million miles. So what is the sun's horsepower? So to answer this question, we have to first pretend that the sun is inside of a sphere with a radius equal to the Earth's distance from the sun. So the inside surface of the sphere that would encase the sun and the whole solar system up to the Earth's orbit would capture all of the sun's energy. If you think about it, only a very small fraction of the sun's energy actually reaches the Earth. The rest of it radiates out into space. So if we had this sphere that captured all the energy and had the same radius as the distance of the Earth from the sun, then we could say that each square meter of the inside of that sphere would be receiving the same radiant energy of 1,400 watts per square meter. So all we need to do is calculate the inside surface area of the sphere to find out how much energy the sun puts out. So the area of a sphere is 4 pi r squared. The radius of that sphere would be 93 million miles, which we write as 93 times 10 to the 6. You could also write it as 9.3 times 10 to the 7. And we're going to convert the radius into meters because the original unit of radius was written in watts per meter squared. So we want a value in watts. So we want to cancel out meters squared. So the first step in calculating the radius is to find the conversion factor from miles to feet, which is 5,280 feet per mile. The miles will cancel. Now I could have written it upside down. It's the same conversion factor, but it would give me the wrong conversion because I wouldn't be able to cancel out miles. So now the answer is in feet. Then I want to convert feet to inches, so there are 12 inches to the foot. Feet cancel, now we're left with a value in inches. We'll convert to centimeters by multiplying by 2.54 centimeters per inch. This allows us to cancel inches. And lastly, we go to meters by dividing by 100, because there are 100 centimeters per meter. Now you notice the centimeters is in the denominator here, so we can cancel out the numerator there. The final unit is in meters, and the value is 1.49 times 10 to the 11 meters. That's the distance of the Earth from the sun on the average. We take that number, place it in the formula for the calculation of the area of a sphere, square the radius. See, the bracket has a 2 on the outside. That means the number is squared and the unit is squared, multiplied by 4 pi. And we get almost a mole of meters squared. Mole is a number that we're going to use in chemistry a little bit later on. Anyway, it's 2.8 times 10 to the 23 meters squared. The radiant energy hitting the inside of the sphere would be 1,400 watts per meter squared. That allows us to cancel meters squared. So the radiant energy of the sun, the energy output of the sun is 3.9 times 10 to the 26 watts, or almost 4 septillion watts. 400 septillion watts. We're going to convert that to horsepower now, just for fun. There's 745.7 watts per 1 horsepower. So if you have a 1,500 watt hair dryer, it's about 2 horsepower of energy to run the hair dryer. We're going to put watts in the denominator so we can cancel with the watts here. And the sun is 5.28 times 10 to the 23 horsepower. Now I reported that the value is 5.3 times 10 to the 23 because the original value had only 2 significant figures. Now this looks like it might be 4 significant figures, and if I had put a decimal place here, it would be. But there's only 2 significant figures there because you only count the numbers. These zeros count as spacers. There's only 2 sig figs here, there's only 2 sig figs here. This looks like 8 sig figs, but in fact it's only 2. So our answer can only have 2 significant figures, or 536 tillion horsepower. That's the power output of the sun. The next phase of the question is to ask how much matter is annihilated per second to generate this much energy. So we're going to use Einstein's equation, E is equal to mc squared. We're going to rearrange the equation to solve for the amount of mass that is being annihilated. We know the energy output of the sun is 536 tillion. But we're going to go back to this number. We're going to use the wattage because that's the unit we need to solve the problem. And so the energy is in watts. This is the speed of light squared. I looked at the speed of light in my calculator, and I got it from the embedded constants in the calculator. It's the first constant you can find. So it's 2.997248 and 2458 times 10 to the 8 meters per second. I square the speed of light, I also reported watts in its base units. Remember a couple days ago we had a lecture where I explained to you what the base units of watts are. They're kilograms, meters squared per second cubed. Now when I square the speed of light, which has units of meters per second, I also have to square the units. So I get meters squared per second squared, which allows me to cancel meters squared and part of the seconds cubed. So the final units for this, the answer to this question is kilograms per second. That's exactly what I'm looking for. How much of the sun's mass is converted into energy. And for every second that the sun shines, 4.3 million tons of matter is converted into pure energy. So the sun is getting lighter at the rate of 4.3 million tons per second. Moving on to the next board, we're going to have another practice question in working with units. This is a slightly facetious question where I say, if there's 50 chickens on a farm, there are 12 farms in a town, 25 towns in a county, 50 counties in a province, and 10 provinces in Canada, how many chickens are there in Canada? Show your work. Now if you multiply all these numbers, you'll get the answer, but that's not what I'm looking for. What I'm looking for is how you can show that the units will cancel. So the first step, I start off by saying 50 chickens per one farm. That's the first phrase right here, 50 chickens per farm. That's a conversion factor right there. Now how do I write it? I'm going to write it with chickens on top because I want my answer to end up in chickens. So 50 chickens per one farm. And you know, if I had started it with the unit upside down, I could still get the right answer at the end. All I'd have to do is flip all the conversion factors so they can cancel appropriately. But I started with 50 chickens on top. And then there are 12 farms per one town. So that allows me to cancel farms. And there's 25 towns per one county. So that allows me to cancel towns. And there's 50 counties per one province. So that allows me to cancel counties. And there's 10 provinces per one country, Canada in this case. That's not exactly right, but that's not the point. So I cancel provinces, and I'm left with units of Canada and chickens. So, as it turns out in our problem, we have 7.5 million chickens in Canada. So that's showing you how to set up your units properly. That's called dimensional analysis. When you set up your conversion factors, it's a very useful skill in chemistry. The next thing is an explanation of elemental symbols and the concept of isotopes. So the first thing I want you to draw your attention to is that when you draw an atomic symbol, there are 4 corners around the symbol that are useful. The bottom left corner is reserved for writing the atomic number, or how many protons are contained in the atom. The top left corner is reserved for writing the mass number, meaning the sum of protons plus neutrons gives you this number. So lithium has 3 protons and 4 neutrons, so the total mass number is 7. I have an interesting video in my favorites about the Castle Bravo explosion, where this element actually comes into the equation. They did a calculation where they were trying to find the yield of an atomic explosion, and they thought they had a certain amount of lithium-6, but it was also contaminated with lithium-7, I believe, or maybe the other way around. Anyway, they miscalculated the amount of fissionable material. Or fusible material, sorry, it was a fusion bomb, it was a hydrogen bomb. And they were expecting the bomb to give a 5 megaton yield, meaning they were expecting the bomb to be the equivalent of 5 million tons of TNT exploding. Instead, it turned out to be 15 million tons yield. So the bomb was 3 times more powerful than they thought, and it just created a disaster in the area where they had the bomb. It was in the Bikini Atoll, and it destroyed all the equipment they were using to measure. The scientists were trapped in a radioactive cloud and had to be rescued by a helicopter, and everybody got a certain amount of radiation. But they got out, but some people died from exposure. I think there were some fishermen in the area, and they got exposed to the fallout. So they died of radiation burns, or they suffered some kind of health effects as a result of it. Anyway, continuing with our lithium atom, the top right corner is reserved for giving the charge on an atom. So whenever you have an ion, you put that, you represent that charge in the top right corner. And this bottom right corner is for saying how many of the atom is being used in the formula. So for example, in H2O, you have 2 hydrogen atoms. You write the 2 at the bottom right. The next thing I want to look at is the concept of isotopes. And I used carbon as an example. Most of the carbon that we see in nature is carbon-12. And first of all, the name of an atom is given by the number of protons. If something has 6 protons, it's called carbon. But you'll also notice that in nature you can get carbon-12, carbon-13, and carbon-14. 99% of carbon is carbon-12. About 1% of carbon is carbon-13, and way less than 1%, a fractional amount of a percent, is carbon-14, which is radioactive. So this is the stuff they use in radiocarbon dating. But you'll notice that they all have the same number of protons. They all have 6 protons, but carbon-12 has 6 neutrons, carbon-13 has 7, and carbon-14 has 8 neutrons. In actual fact, all the carbon-14 that comes into our atmosphere is made by cosmic rays hitting nitrogen in the upper reaches of the atmosphere. So when a cosmic ray goes hurtling through the cosmos, it's a high-energy particle traveling close to the speed of light. When it hits the molecule of nitrogen, it actually shatters part of the molecule, and the molecule converts into carbon with extra neutrons. And it's radioactive because the nucleus is relatively unstable compared to carbon-12 and carbon-13. So that's where we get our carbon-14. And plants will incorporate carbon-14 just like they incorporate other forms of carbon, but that causes a slight amount of radioactivity in all living things. And that radioactivity can be measured, and it tends to decay after the object dies because it's no longer incorporating new carbon. And as the radioactivity decays, you can measure that radioactivity and use it as a way of gauging the time when the object stopped living. So if it's a tree or a flower that was preserved, you could use it to predict the age of objects up to about 2,000 years since they've died. So it can be used for dating artifacts that are made of wood or paper. So all these are carbon atoms because they have 6 protons. This group of the same type of atom but with different numbers of neutrons are called isotopes. And the isotopes are distinguished by the fact that they have differing numbers of neutrons but the same number of protons.